All right, so we've talked about matrix games, and in section 8 we found that if the game is strictly determined, you can solve it by inspection. You look for the minimax, how does it work? Minimax column values and the max-min row values. Or you look for values in the rows, find a value that's both a minimum in its row and a maximum in its column. Right? Now, in some cases, games are not strictly determined, and you have probabilistic strategy, and in section 9 there's found some formulas for 2x2 games. So in section 11, the next section, we'll discuss how to use linear programming to solve arbitrary games. So this section is kind of an intermediate section where we find some special matrix games in case one of the player has just two strategies. So it would be a 2x(n) game or an n/2 game. And in this case, you can use a geometric method. All right. So let's do an example here. Suppose that Jones conceals one of the following 4 bills in his hand, a 1 or 2 United States bill or a 1 or 2 Canadian bill. So we're guessing that these US and Canadian bills have exactly the same value, which is not exactly true, but it's close enough. Smith guesses either US or Canadian and gets the bill if his guess is correct. Otherwise, he doesn't get it. Okay. So we assume that a Canadian dollar has the same real value as a US dollar. The matrix of the game is as following. All right, so you can see that Jones is going to lose. He's either going to lose something or he's not going to lose anything. Certainly, Jones is not going to come out ahead, so it's not a fair game, but it is a zero-sum game. And here's how it works. If Smith guesses correctly, then he gets the value, and Jones loses the corresponding value, US and Canadian. Otherwise, Smith gets nothing. Right. Now, if you look at it, Jones always does better by using the $1 bill. You see why that is? Because whether or not it's $1 or $2 American bill, Smith is going to win it if he guesses US. Right? So why not put in the $1 bill and he'll only lose 1? No reason to put in the $2 bills. That's a gratuitous loss. Same with Canadian. No reason for Jones to choose $2 bill, because if Smith guesses US, he won't lose it. But if he guesses Canadian, he's going to lose $2 instead of $1. So these two strategies are useless. The -2, 0 and the 0, -2. Those two strategies are useless. We can just take those out. These are called dominated strategies because there's a strategy that's always better. We found a dominated strategy in the previous example also, where one strategy was always better than another. So no matter what Smith guesses, this strategy here is better than this one. And no matter what Smith guesses, this strategy is better than this one. So we can throw out the worst strategy. The mathematical definition of dominated strategy is as follows. We say that row I dominates row H if every entry in row I is larger than the corresponding entry in row H. Now, we can also have dominated column strategies. Column J dominates column K as every entry in column J is as small or smaller than the corresponding entry in column K. So that means that you'd always choose column J instead of column K. Don't even need to consider column K. So that's a good way to reduce your options and get an easier matrix. All right. So here's another example. Consider this game where you've got a bunch of options. Player 1 has only 2 options. Player 2 has several options. Can we find any dominated strategy? Remember, player 2 wants the smaller values. Well, this one does not dominate this one because this is smaller than this one, but this one's not smaller than this one. Let's see. But if you look at column 4, this 0 is smaller than this 0, this -2 is smaller than this 2. So the column player is always better off choosing column 2 instead of column 4. So column 4 is useless. Right. None of the others dominate, so we can leave 3 strategies here. Right. Now, at this point, we're kind of run out of our previous methods. We got to come up with a new method. All right, so here's how we reason. Right, now, suppose that player R announces he's going to use a certain mixed strategy, P1, P2. Now, these are probabilities, so they have to add up to 1. So P1 has to be equal to 1 minus P2. So we can always write this strategy as 1 minus P2 and P2. Right, where P2 could be any number, 1/6, 1/2, 1 over square root of 2, and so on. All right, assume for the moment that player C knows R will use this strategy. Then he can compute his expected payment from choosing each of the following alternatives. All right, if he chooses column 1, well, let's look at what happens when if he chooses column 1. Okay. If he chooses column 1, he's going to get 1 with probability P1 and minus 3 with probability P2. Right? So we can write that as 1 times P1 minus 3 times P2. Now remember, P1 is 1 minus P2. So you can substitute in 1 minus P2 for P1, do a little algebra, and you get 1 minus 4P2. On the other hand, if the column player chooses column 2, what's his payoff going to be? Well, we know that the row player chooses this with probability P1, this minus 2 with probability P2. So his payoff is going to be P1 times 0 plus P2 times minus 2. Okay. That's his expected payoff. Now, he's not always going to get that, but over the long run, if you consider the probabilities, that's what his expected payoff is going to be. So we get this, column 2, y equals 0 times P1 minus 2 times P2. So this is what he gets if he chooses column 2. You can figure out the same thing for column 3. You end up with minus 1 plus 2 P2. Right. Now, each one of these expected payments is a function of P2. So these give us 3 different lines. All right, 3 different payoffs corresponding to the 3 different possible choices of the column. We're only interested when P2 is between 0 and 1, because P2 is a probability. You can't have a probability of more than 1 or less than 0. So let's plot these 3 lines between P2 equals 0 and P2 equals 1. So here's the P2 axis, P2 equals 0, P2 equals 1. And here are the 3 lines, 1, 2. So this is for column 1, this is for column 2, this is for column 3. So you just plot these lines. Y is a function of P2. Now remember what these lines mean. These lines give the payoff for the column player if he plays that particular column and the row player plays his mixed strategy P1, P2. Right? So which column is the column player going to choose? Well, the column player wants to minimize his losses because Y represents his losses. Y is the payoff to the row player. So this solid line represents the payoff to the column player if he chooses his best strategy associated with the row player's mixed strategy. In other words, if the row player chooses a mixed strategy with choose mixed strategy with P2 equals 1/4, then the column player will not choose this row column 1 because then the payoff's 0, which is too large. He could choose either column 2 or column 3 and get a payoff of minus 1/2, which he likes. That's a good payoff for him. On the other hand, if the row player chose P2 equals 1/2, that looks like about here. If the row player chose P2 equals 1/2, then the column player would choose either column 2 or column 1, and he'd get a payoff of minus 1. That's even better. So it seems like this would be a better option than this one. However, the row player can choose. The row player can choose what his strategy is going to be. Now the row player's thinking, I want to maximize my payoff. Now if I choose this mixed strategy, then that gives me the biggest minimum payoff. Or I should say, that's going to give the row player the biggest payoff if the column player so chooses to minimize the row player's reward. So this really is the role player's best option, because he wants to maximize the payoff considering what the column player is going to play. All right, so this 1/4 is going to be the role player's probability for his mixed strategy. This is going to be the role player's P2, and the role player's P1, of course, is going to be 3/4 because P1 plus P2 has to be equal to 1. So 3/4 of the time, the role player is going to choose P1, and 1/4 of the time, the role player is going to choose P2. So that's what it says here in the text as well. The role player's optimal strategy is 3/4 times chooses row 1, 1/4 time chooses row 2. Now what about the column player? Let's look at this graph. At this point where P2 equals 1/4, the column player chooses either, this is column 3, and this is column 2. He doesn't choose column 1. Column 1 is out of the picture. Only column 2 and column 3 are in the picture. Right? So what mix is he going to choose of column 2, column 3? Well, at this point, since we only have column 2, column 3 in the mix, we can ignore column 1 and we get a 2x2 game. And we can use the 2x2 formulas in the previous section and get this for our column player's optimal strategy. All right. Now, since as I said, the column 1 and column 4 are useless, we can put zeros for those, and we get our total optimum strategy for the column player as 0, 1/2, 1/2, 0. Okay, well, that's good for this video. We'll continue with the next video.